Chemistry 1311, General Inorganic Chemistry 1. Chemistry, the molecular nature of matter and change. In Chapter 1, we're going to study some fundamental definitions, the chemical arts and the origins of modern chemistry, the scientific approach, developing a model, measurements and chemical problem solving, uncertainty in measurements, significant figures. Chemistry is the study of matter, its properties, the changes that matter undergoes, and the energy associated with these changes. Matter is anything that has both mass and volume, the stuff of the universe. For example, books, planets, trees, professors, and students. Composition is the types and amounts of simpler substance that make up a sample of matter. Properties are the characteristics that give each substance a unique identity. A substance may have different phases: solid, liquid, and gas phase. A solid has a fixed shape and volume. Solid may be hard or soft, rigid or flexible. For example, ice is a solid and hard. Rubber is flexible. Cotton is soft. At the microscopic level, the atoms or molecules that make up this solid are very close together. There's a strong intermolecular interaction between these molecules. And due to this strong interaction, solid has a fixed shape and volume. A liquid has a varying shape that conforms to the shape of the container, but a fixed volume. In other words, liquid volume is fixed, but the shape can change. This is because at the microscopic level, the atoms has moderate interaction, and this interaction give a fixed volume, but the shape can change. A gas phase has no fixed shape and volume. At the microscopic level, the atoms or molecules are far away from each other, and the interaction between these molecules are very small. And because they have very small intermolecular interaction, the molecules can change the shape and the volume. A substance may have different properties: chemical property, physical property. Physical properties are the properties a substance shows by itself without changing into or interacting with another substance. For example, ice melts at 0 degrees. Ice does not need to react or change to anything else. Okay, it's the water molecule, right? Melt at 0 degrees itself. Similarly, water boils at 100 degrees. Okay, so the color, melting point, boiling point, density, these are the properties that the substance shows by itself, okay, without changing or interact with anything else. Chemical properties are the properties a substance shows as it changes into or interacts with other substance. For example, natural gas is flammable, which means that CH4, that's the natural gas, react with oxygen, forms carbon dioxide and water plus heat. So because it generates a lot of heat, and that is responsible for the flames. Okay, so this flammability is associated with this chemical reaction to change methane into something else. Similarly, iron rust, okay, means that iron react with oxygen, forms iron oxide, okay, or iron 2O3, iron oxide. So these are the responsible for the rust of iron. So this property is related to the chemical reaction. react with oxygen, and these are chemical properties. This diagram shows the distinction between physical and chemical change. On the left side, we show a physical change from solid ice to liquid water. Okay, it's a phase transition. If we look at the microscopic level, in ice, we have water molecules here. Okay, the red one is oxygen, the blue one is hydrogen. Okay, so each oxygen connect two hydrogen, so that's water molecule. And you can see these water molecules pack uniformly, very ordered, okay, strong interaction. So in fact, it has a hydrogen bond. So this strong interaction is responsible for the solid state. Now, when they melt into liquid water, the molecules are the same, still water. If you look at it, oxygen, hydrogen, hydrogen. So it's still H2O, but they are not so as ordered as the solid state ice. All right, and you still have some hydrogen bond, but less than solid state. So interaction becomes weaker, and that's why water can change shape. But at the microscopic level, the composition doesn't change. Okay, the only change is the interaction. So this is called the physical change. Okay, if we look at the right side, and this is a chemical change. To change water molecule, here is water, to oxygen gas and hydrogen gas by electricity. So by applying electricity, water becomes hydrogen and oxygen. Okay, and that is a chemical change. Sample problem 1.1. The scenes below represent an atomic scale view of substance A undergoing two different changes. One goes to B, one goes to C. Decide whether each scene shows a physical or chemical change. In order to decide whether physical or chemical change, we need to know whether composition change. And the composition can be determined by looking at the numbers and the colors of the little spheres, okay, before and after change. If the composition does not change, then it is physical. If the composition changes, then it's a chemical change. Let's first look at the change from A to B. In A, there are molecules that consists of three atoms, two red, okay, two reds, and one blue. Again here, two reds, one blue, two reds, one blue. So these are the molecules in A. In B, there are molecules consist of two reds, or one red, one blue, one red, one blue, two reds, and therefore the composition change before and after the change, and therefore this is a chemical change. Let's now look at the change from A to C. Again, in A, molecules consist of three atoms, two reds, one blue. Okay, three atoms, two reds, one blue, two reds, one blue. Now in C, again, you see molecules, two reds, one blue, two reds, one blue. So there's many molecules. All right, the only difference is the distance between the atoms. In C, they are packed more closer. Okay, so it's probably a solid state. And this one may be a gas, so it's the phase transition. And the composition doesn't change, and therefore it's a physical change. We already mentioned several times that phase transition or change of state, that's phase transition, is a physical change. This is because the composition doesn't change. Composition doesn't change. The only change is physical form changes. So the intermolecular distance. So in gas phase, they are farther away. In the liquid or solid phase, they are closer. They are more packed, more ordered, uniform. Okay, that's the physical form change. All right. Now, the change in physical state or physical change are reversible. These changes can be brought about by temperature change. For example, at very low temperature, okay, water is freeze to ice. So ice at very low temperature. When you increase temperature, ice may melt into liquid water. All right, if you increase temperature further, eventually it will boil and become steam. Okay, gas phase. So you can this physical state change can be brought about by temperature change, and it's reversible. If you cool it down, then steam can condense to water, water can freeze to ice. Okay, but for a chemical change, it's not reversible. If iron rust to water to iron oxide, iron oxide cannot simply reversed by temperature change. Here shows some characteristic properties of copper. Now, copper is a metal that is malleable. Okay, so you can easily hammer into sheets like this one, or drawn into wires. Okay, so this is a physical property because the composition doesn't change. It's still copper atoms. All right, you just change different shape. Now it can melt, so it's a physical property. And after melt, it can mix with zinc to form brass. Note that in brass, copper and zinc, they don't react. It just mix uniformly together. Okay, so it's a physical property, not a chemical property. And density, melting point, boiling point, these are all physical properties. Now, copper can slowly form a blue-greenish carbonate in moist air, and this is because copper reacts with carbon dioxide, water, and forms something else. So, because there's a chemical reaction involved in this property, so this is a chemical property. And it can react with nitric acid, sulfuric acid. So again, involves chemical reaction, and slowly forms a deep blue solution in aqueous ammonia. So again, involves chemical reaction. So this is chemical properties. Sample problem 1.2. Decide whether each of following process is primarily a physical or chemical change, and explain briefly. So to determine whether a change is physical or chemical, we need to know whether substance change composition. In question A, frost forms as temperature drops on a humid winter night. So this change involves condensation of water. The composition doesn't change. It's water molecule. It's just change different phases, and therefore it's a physical change. A corn stalk grows from a seed that is watered and fertilized. A plant grows through photosynthesis, which is a chemical reaction, and so it's a chemical change. A match ignites to form ash and a mixture of gases. So apparently the match, head of the match react with oxygen to form different substances. So it's a chemical reaction, so chemical change. Perspiration evaporates when you relax after jogging. And this involves water vaporize, and so it doesn't have composition change, and therefore it's a physical change. A silver fork tarnishes slowly in air. And this is similar to iron rust. Okay, silver also rust. It reacts with oxygen, okay, tarnish, and therefore it's a chemical change. Physical and chemical changes are accompanied by energy changes. Energy is often defined as the ability to do work. There are two types of energies: potential energy, kinetic energy. Potential energy is the energy due to the position of an object. In physics, you learned that potential energy is calculated by mgh due to the gravitational force. M is the mass, g is the gravitational constant, h is the height of the object. So the higher the object, the more potential energy it has to do work. Kinetic energy is energy due to the movement of objects. In physics, kinetic energy is calculated by half mv squared. V is the velocity. So the faster an object moves, the more kinetic energy it has. The total energy is calculated by the sum of the potential energy and the kinetic energy. Energy is conserved. It can be converted from one form to another form. For example, from kinetic energy to potential energy, or potential energy to kinetic energy. In the next slide, we'll show you an example that lower energy states are more stable and favored over higher energy state. Here shows an example of energy conversion between kinetic energy and potential energy for a gravitational system. When an object is pulled up, the potential energy increases. Okay, remember potential energy is mgh. So the higher the object, the more potential energy it has. Now, if you let this object go, it will go down and becomes faster and faster. And so during this process, the potential energy is converted to kinetic energy until it hits the ground. At this point, the potential energy becomes zero. Now, because the object always wants to go from high to low, so the object on the ground, which has the lowest potential energy, is the most stable state. Well, at the highest point, has the highest potential energy, but the least stable, because it always wants to go down. Here shows the energy conversion of a system with two balls attached by a spring. When the two balls are pulled apart, potential energy increases. When they are released, they try to go back to the relaxed state. So the two balls move towards each other, increase kinetic energy. So potential energy is converted to kinetic energy until it becomes a relaxed state where the potential energy becomes minimum. Now, during the whole process, the energy is conserved, potential energy and kinetic energy. When two opposite charges are separated, they have a potential energy, and they are pulled towards each other due to the attraction force. So potential energy is converted to kinetic energy. The less distance they are, the lower the potential energy and the more stable the system is. A fuel is higher in chemical potential energy than the exhaust. This is due to the difference in the chemical structure and the chemical bonding. As the fuel burns, some of its potential energy is converted to the kinetic energy of the moving car. A car full of gasoline has the highest potential energy. When all the gasoline is converted to exhaust, the car has the least potential energy and cannot move. In that sense, it's more stable. This table shows SI units for some common quantities. Mass SI unit is kilogram. The abbreviation is kg, kilogram. Length is meter or m. Time, second, s. Temperature is Kelvin or K. Amount of substance is mole or mol. Electrical current, ampere, A. Luminous intensity is candela, CD. This table shows common decimal prefixes used with SI unit. Let's use meter as an example. So meter is abbreviated as M. If we add a kilo or K, so km, and that means it's 10 to the third power meter. Okay, or 1000 meter. Okay, so 1 kilometer is 1000 meter. Similarly, mega, so 1 megameter, so you use capital M. And that 1 megameter is 10 to the 6th power meter. All right, 1 gig or G meter is 10 to the 9th power meter. And tera means 10 to the 12th power. On the other side, a decimeter, okay, D, so dm means 1 decimeter, which is 0.1 meter. So it's much less than 1 meter, okay, or 10 to the minus 1. Centimeter, so 1 centimeter, C, centimeter means 0.01 meter. So it's much less than decimeter or meter. And then when we go to 1 milliliter, so milliliter, so m milliliter, millimeter, which equals 10 to the negative 3, okay, meter. Okay, micrometer, mu, so mu m, that's 1 micrometer, which is 10 to the minus 6th power meter. Nano means 10 to the negative 9, and pico means 10 to the negative 12. This table shows common SI English equivalent quantities. For length, as we already know, the SI unit is a kilometer. 1 kilometer equals 1000 meter. 1 meter equals 100 centimeter, and 1 meter equals 1000 milliliter. 1 centimeter equals 0.01 meter. Length also have other units, such as mile, yard, inch. These are called English unit. Here shows the conversion factor between English and the SI unit. 1 mile equals 1.609 kilometer. 1 inch equals 2.54 centimeter. For volume, the SI unit is cubic meter. 1 cubic meter is 10 to the 6 cubic centimeter. 1 cubic decimeter equals 1000 cubic centimeter. And this is because 1 decimeter equals 10 centimeter. So 1 cubic decimeter should be 10 to the 3rd power cubic centimeter. Now, volume also have other units, cubic feet in English, gallon, and quarts. And these are the conversion factor between English and SI unit. For mass, SI unit is a kilogram, and English unit is pounds. So 1 pound equals 0.4536 kilogram. To see why 1 cubic decimeter equals 1000 cubic centimeter, we look at this diagram, which is a cube with length 1 decimeter, width 1 decimeter, height 1 decimeter. And because 1 decimeter is 10 centimeters, so this is 1 centimeter, 1 centimeter. You have 10 of them, so it's 10 centimeter. And the length width is also 10 centimeter. Height is 10 centimeter. And therefore the volume is 10 times 10 times 10. And that gives you 1000 cubic centimeter. Now in chemistry, we have another preferred unit for volume, and that is liter. 1 cubic decimeter equals 1 liter. Okay, this is an important relation, and you need to remember that. Okay, 1 cubic decimeter equals 1 liter. Now 1 cubic decimeter equals 1000 cubic centimeter, and 1 liter equals 1000 milliliter, because milli means 10 to the minus 3. So 1 milliliter should equals 10 to the minus 3 liter, and therefore 1 liter is 1000 milliliter. And therefore this gives another relation, which is 1 cubic centimeter equals 1 milliliter. Okay, so 1 cubic decimeter equals 1 liter, 1 cubic centimeter is 1 milliliter. Similarly, 1 cubic millimeter equals 1 microliter. This diagram shows some common laboratory volumetric glassware. Two graduate cylinders to measure the volume of a certain liquid. A pipette is used to transfer a certain amount of liquid into a beaker. A burette is used for titration in an Erlenmeyer flask. Two volumetric flasks are used to make a certain concentration of solution. Automatic pipette is used to, again, to transfer a fixed amount of solution. This diagram shows the relative quantities of length, volume, and mass. For example, the height of Mount Everest is between 10 to the third power and 10 to the sixth power meter. The distance from Earth to Sun is between 10 to the 9th power and 10 to the 12th power meter. The thickness of average human hair is smaller than 1 milliliter, and the size of red blood cell is smaller than 1 micrometer, or 10 to the minus 6, so it's very small. The diameter of an atom is smaller than 1 nanometer, or 10 to the minus 9. The volume of ocean and the seas of the world is between 10 to the 21 to 10 to the 24 liter. The volume of blood in average human is between 1 and 1000 liter, and the baseball is between 10 to the minus 3 to 1 liter. A typical bacterial cell has a volume between 10 to the minus 15 to 10 to the minus 12. All measured quantities consist of a number and a unit. For example, 10 meter. 10 is a number, meter is a unit. Units are manipulated like numbers. For example, 3 feet times 4 feet. That's to calculate an area. So here you have a rectangle, and the width is 3, the length is 4. So the area is 3 feet times 4 feet. And to calculate the area, we can just combine numbers first. So 3 times 4 is 12. And combine the unit feet times feet is feet squared. Okay. And similarly, 350 mile per hour. So you use distance divided by time, that give you velocity. All right, and you can combine numbers. 350 divided by 7, that is 50 divided by 1, and mile per hour. So you can write 50 mile per hour. A conversion factor is a ratio of equivalent quantities used to express a quantity in different units. The idea is that anything times 1 doesn't change the value. For example, 10 times 1 is 10, so 10 is still 10, or 12 times 1 is still 12. Okay, now if we know a relation, this relation, 1 mile equals 5,280 feet, then the ratio 1 mile over 5,280 feet is 1, because 1 mile equals 5,280. These two are equivalent. If you use two equivalent numbers divided by itself, you get 1. For example, 5 divided by 5 is 1. So this is 1, and this is called a conversion factor. So that's called a conversion factor. Now, how do you use this conversion factor? Well, suppose we want to know 1,0,560 feet is how many miles. Okay, note that we want to convert feet to miles. How do we do that? Well, we can multiply by this conversion factor. So 1,0,560 feet times this conversion factor, 1 mile over 5,280 feet. Remember, this is equivalent to 1 because 1 mile equals 5,280. So it's equivalent to 1. So it doesn't change the value. However, it will change the unit because you can see here, you have a feet here, you also have a feet here. And therefore, the unit only have mile left. That give you unit mile. It changed feet to mile. But how many miles? Well, you have 10560 divided by this number 5280, and that give you 2 miles. And therefore we convert 10560 feet unit feet to mile, so to 2 miles. A conversion factor is chosen and set up so that all units cancel except those required for the answer. Let's use this relationship again. 1 mile equals 5,280 feet. We can write two conversion factors. One is 1 mile divided by 5,280 feet, as we did in the last slide, because these two are equivalent, so it's like 1. Okay. Another way to write is 5,280 feet divided by 1 mile. This is also a conversion factor because the denominator numerical are the same. All right, so it's 1. So which one do we use? Well, it depends on the question. If we want to change feet to miles, okay, then we have to cancel feet, and so we should choose this one, so that feet can be cancelled, and this will be left miles. Okay, so in this case we write 3,212 feet times 1 mile over 5,280 feet. So feet cancel, and that gives you miles. On the other hand, if we want to change 100 miles to how many feet? Okay, how do we do that? Then we need to choose this one. So it should be 100 times miles. 100 miles times 5280 feet equals 1 mile. Okay, then you can see mile cancel, and you get 5280 and then plus 2 zeros, feet. So feet left. Please read the textbook chapter 1 to the section of units and conversion factors in calculations. For 8th edition, it's the page 19. Work on the follow-up problems.